All right, y'all. Last video here for the welding section. We're going to cover in this video resistant spot welding and common welding joints. So without further ado, let's jump in. So we're going to be moving away from electric arc welding now, and we're going to be talking about one other way that we can use electricity to weld materials, but without using an electrical arc. That is called resistant spot welding, or resistance welding as a general term. Resistance welding is accomplished when current is caused to flow through electrode tips into separate pieces of metal being joined. The resistance, basically what happens is when electricity is pushed through these tips of the welder, it is forced through this piece of material, and as electricity is forced through a piece of material, it faces what we call resistance. Metals inherently are resistant to electrical flow. When electricity faces resistance, it generates heat. And so the idea behind resistance welding is that we force electricity through two pieces of metal. It generates enough heat that it melts or fuses the metal together into one piece. Resistance welding works very well on metals with high electrical resistance, low thermal conductivity, or low melting points. And so we will be using resistance welding in our lab, but it's oftentimes used in thinner materials like sheet metal welding. The most common type of resistant welding is resistant spot welding, or RSW. And it's when two electrodes, oftentimes that are copper in composition, apply current and pressure to two pieces of material for a designated time. So you can see here is a resistant spot welder on the left, has two big tongs that come out with tips over here on the far left. And over here on the right, you can see the schematic. You have the welder here that produces electrical current. Current comes up, down through this copper electrode. It wants to jump through this metal to the other one to get back to the welder. So as electricity flows through one copper tip through that metal, it generates a lot of heat that will fuse those two pieces of metal together. Current then comes back to the welder. Those tips also apply enough pressure to hold the material into intimate contact while the electricity is flowing. Back over to the welder here on the left, the dial down here at the bottom sets your amperage. There's also a timer on the front of the welder that you can set the designated time for the welding operation to occur. Okay? So when we're thinking about resistant spot welding, there's really three factors that can affect the quality of the resistant spot weld itself. The first two are here in bold, is the weld current and time. The weld current is proportional to the weld time. Thicker materials require a higher current and a higher time. So typically if you increase the current, you need to increase the time. Thinner materials require a lower current and a lower time. The ideal time and current conditions are somewhere between the level of material of causing metal to be expelled. So what you want to see is when you weld, you want to see the material turn red around the tips, and you want them to stay red. Okay? If you're not seeing red around the tips, you probably need more current and more time. If you have too much current or too much time, you will see the metal being expelled or blown out of the weld joint in the form of sparks. In that case, you will likely want to reduce the current and reduce the time. Some folks may reduce one or the other. I typically reduce the current, leave the time the same when I see metal being expelled from the joint. Okay? So keep that in mind when you're welding. If you see a bunch of sparks coming out, you probably need to turn down the current of the machine. Okay? Those are two real adjustments that you can make with a resistant spot welder. The last factor is pressure. The pressure that's applied by a resistant spot welder, the tongs on it, are used to hold the parts in intimate contact at the joint interface. You want the two pieces of metal to be touching each other with slight pressure. Pressure should not be used to pull the work pieces together. The tongs on these resistant spot welders are copper in composition. They're pretty ductile, so you don't want to use this really as a clamp. You want to use this just to apply slight pressure to the joints themselves. Okay? So, materials that can be spot welded are mild steel, low alloy and medium carbon steel, stainless steel, aluminum, and galvanized sheet steels. Aluminum. Those four you can spot weld. Most oftentimes it is thinner, mild steel. Galvanized sheet steels should not be spot welded. The problem when welding galvanized sheet steel is that the galvanization, remember that's that zinc coating, will melt onto the tips and cause issues. It will also generate enough heat to melt the galvanization, which will basically take away its corrosiveness resistance of that piece of material. So real quick, I'd like to show you what a resistant spot weld looks like so that you know what you're looking at. So here underneath the document camera, you can see I have two pieces of metal that were spot welded. How it gets to coin the name spot welding is it makes a little spot of weld at each of these locations. So I got two pieces of material that are lap. It's called a lap joint when they put one over the other, and they were welded. These are the copper tips. So these copper tips would go around the weldment like this. Electricity would pass by at a certain current for a given time. Once that time has been released, you allow the metal to cool, and then you can release the pressure from the joint. Most of these spot welds are really nice. This one over here has a little bit of material being expelled from the joint. It could have had a little bit too much time on that weld, but these other ones deem appropriate. Again, resistant spot welding is really a good way to join thinner materials together. The other cool thing about resistant spot welding is it doesn't produce any arc, so therefore you don't need a welding helmet. You just need a good set of gloves to handle the material as it heats up. All right. To wrap this up, we're going to finish up talking about some common welding terminology that you'll hear me discuss and you'll hear others discuss as you make your way through your time welding. The first of those is the joint. And the joint is how the materials pieces mate. So you could have a T-joint, okay? You could have a lap joint, which I just talked about when two metal pieces overlap one another. You can have an edge joint. You can have a butt joint. And those are just the common joint, they call joints. It's how the two pieces of material come together, what angle they come together, and how the surfaces mate. The groove itself is the profile of the mating surface. So is the groove flat? Is it rounded? That's the profile of that surface. And the last main welding term that you'll hear us talk about is bevel. When you have thick pieces of material, the weld joint may not be able to penetrate through. So in order to improve the penetration of that piece of weldment, you need to do what we call bevel. And when you bevel a piece of material, you take an angle grinder and you cut an angle across the edge or the groove of that material to reduce the initial thickness which the welder must burn through to create penetration. So when you're welding thicker materials, I'd say anything much over 1/8 of an inch, you would want to bevel that material on the edge at a pretty sharp angle and then apply multiple weld passes until you build back up to the surface of that weld joint itself. So here I'll show you real quick what a bevel looks like. This is not the best example, but it's the only one I have with me. And so here we have two pieces of material. Two pieces of flat bar look to be about 1/4 inch thick. If I was going to weld this, if I weld it, see how thick that is? If I put these two pieces together like this, without any gap, I'm only going to be welding the surface. It's not going to have a solid weld. Now, I could gap these slightly, and that would help the weld penetrate throughout. However, because this is a flat side here, it's just going to penetrate part of the way through because it's so thick. So what I can do is I can go over to a grinder and I can cut an angle on the edge, and this is called a bevel. You really want to cut this down to about halfway or at least about 1/8 of an inch thick before you start to weld. So then what you can do is you can simply put this together, and you want to gap this approximately about 1/16 of an inch or so, just enough for the weld bead to go through and touch the two pieces. And then what this bevel does is allow you to layer welds in here to create a weld. You have multiple passes through here to create a solid weld that goes the thickness of the metal instead of just laying on the surface. So that's the purpose of a bevel. For our purposes in class this semester, you will be welding thin enough materials that you don't have to worry about beveling. But if you do a certification or something like that, you will have to worry about beveling the material. So we'll wrap up by talking about the common welding joints that you'll see. Butt joint is when two pieces of metal are in the same plane. Corner joint, when they form a right angle at the corner. T-joint, they form a right angle in the form of a T. Edge joints, when two pieces of metal are parallel, you weld the edge. And the lap joint is when two pieces are overlapped. This is better explained pictorially, shown here. Here's your butt joint, two pieces together, flat on the table. Lap joint, two pieces overlapping. T-joint, 90 degrees in the center. Edge, two pieces pushed together, you weld the edge. And then a corner joint is 90 degrees on the corner of two pieces of material. Okay, y'all, we've covered a lot of ground. This is the end of the welding section. So by now, just a quick recap, what we've discussed. We've discussed what welding is. We've discussed how to use a torch and how to use it safely. We've talked about oxyacetylene welding. We've talked about mechanical bonding techniques, which are brazing and soldering. We talked about electric arc welding and polarities that we use with each. We spent a video talking about stick welding, video talking about wire welding processes, which is flux core and MIG. We've talked about TIG welding, and now we've talked about resistance spot welding and some common welding terminology. So by now, you should have a basic understanding of all these welding processes, when it's advantageous to use one over the other, and a little bit of information about how you would apply it. Moving forward, we will move into lab where you'll have a chance to practice most of these techniques that we've discussed in a very introductory format. So with that, we will conclude this video, and I will catch you all in the lectures for next week, which deal with mechanical fasteners. Take care.